Okay, let's start. So thank you everybody to join our webinar. This week will be for telerobotics with force feedback. Hi, I'm Pierre Verkreuz. I'm in charge for sales and business development. And Jerome Perret will join me for the technical part of this presentation. So before we start, please, we are a large number of people attendees, so please keep your microphone off and switch off also your webcam, please. You can use the WeChat, you can use the chat, so anytime that you have a question, please write it, and at the end, we will have a Q&A part of the webinar. So yes, next. The seminar will be short introduction about the company, some reference and product. And after, I will pass the word to Jerome, who can continue on telerobotic and use case. And we'll come back from the Q&A. So Haption, so we are a French company. The company is born in 2001. We come from CEA, French Nuclear Agency, the robotic lab. We are located in the west side of France, and we have an office in Germany, but we have many partners everywhere in the world. So we deploy system everywhere, Asia, US, North America, South America. So depending based on our partners. So we are key partners from Dassault System and Siemens PLM. We didn't talk too much about this part today. It's more for simulation and how we could use haptic to do force feedback clashing in the virtual environment. We will talk more a little bit on telerobotics. So that's today we are partners of so we are UR plus partners. This, you see the numbers last year. So we do more than 2 million euros, mainly 30% is from France, 30% is other country in Europe, and 30% is nearly worldwide. So we are really a small company. We are 15%, but really focused on development of hardware and integration of software. See the reference. So we have reference, like I told you, everywhere in the world. And on different industry, we are in aerospace, Airbus, Comac, transport, car, and trains, CRC, Daimler, Jaguar, Renault, Peugeot, nuclear with Orano, UKAEA, Thales Alenia. So yeah, we are really on different style of industry and large in the world. Also, we still have a lot of contact with the university and research. We deploy system there, and also they give us a lot of input to increase our portfolio in hardware and give us a lot of ID. Also, you see a lot of reference everywhere, Belgium with Germany, Braunschweig, Darmstadt, UK, UCL, Italy, Politecnico of Milano, Deakin in Australia. Yes, so we have a large numbers of reference in the world. So this is the list of products. I do only concentrate everything on one slide. So coming from the desktop is the wrist size and low force. And as you go to the right part, you see we extend the workspace. So the Virtual 6D TAO, it's the size of your arm. And the scale 1 can permit to extend the workspace on a large room. On the software, so we have the basic SDK called Virtuose SDK. On top of this, we integrate with a collision detection engine called IPSI, and it's on which we develop the interface with the Dassault and Siemens product. Also, our customers develop their own application based on IPSI or on their own physical engine. And today we will talk a little bit more about how we develop a portfolio for robotics and force control system. So now we change the world. So now it's Jerome that they will continue the discussion, and I will come back later.
Thank you, Pierre. Also, welcome from my side. My name is Jerome Perret. I'm the one of the two founders of the company Haption, and today CEO, and dealing with the development of what we are going to show you later on. But first, I will go through an introduction of what we understand at Telerobotics with force feedback, and give you an overview of the use cases we are looking at. So what is Telerobotics? There's a good definition on Wikipedia which says that it's the control of semi-autonomous robots from a distance and a combination of teleoperation and telepresence. And the scientific foundation comes from a paper, a very famous paper by Thomas Sheridan in the journal in '88. So it's not a new concept. And basically what it means is that you have an operator and a robot. The operator controls the robot, meaning that the operator gives a direction, speed, and a force, or some combination of those. That's the teleoperation side. And the robot feeds back information to the operator, again, direction of movement, speed, force, or combination. And the added thing is that the robot itself has also a form of semi-autonomy. One of the possible autonomy is the use of virtual fixtures, which are a way to simplify the work of the operator by freezing some degrees of freedom. So that's the concept of telerobotics. And now what about force feedback? So there are two main contributions of force feedback in the field of telerobotics. There's the first I call dynamics feedback, which is feeding back to the operator the behavior of the robot. If you want an analogy, is the feedback on your steering wheel when you drive your car. So you know that in case you lose that feedback because the road is slippy, then you basically mostly lose control unless you have specially trained for that. So that's really the dynamic feedback, which is very important and does not really depend on sensors on the robot. And then there's a second contribution, which I call interaction feedback, which is the feedback from sensors on the robot, feeding back the weight, inertia, the friction when you have contact, the reaction forces. So all those aspects which can be measured in the remote environment by the slave robot and fed back to the operator. So those are the two main contributions of force feedback, and we'll see that they don't have exactly the same requirements, constraints, and the same role. So what are the main challenges when you develop a telerobotic system? First, there are robotic functionalities. So you need Cartesian space master slave control because most of the time your slave robot and your master robots don't have the same kinematics. So mapping the joints of one to the other is problematic, all the more so as they often don't have the same numbers of joints. So the easiest way to solve that is to use Cartesian space control, which means controlling a displacement in space, position, orientation. Then you have the problem of controlling the redundant actuators in case your slave robot has more joints than the number of degrees of freedom you want to control in Cartesian space. That's called null space control. Then you have the compliance of the master and slave, the force compliance, which is critical for force feedback. If your slave robot is not compliant, not force compliant, then you will need force sensors measuring the effect on the environment or the weight of objects if you want to feed back the information to the operator. you always have to cope with scaling of movement, scaling of forces, and then the virtual features I already mentioned. So those are the pure robotic functionalities, but it's not enough. You also have to face performance constraints. First of all, because you're dealing with robots, you have to have a very stable real-time behavior of your control system. That's a given. The additional constraint is that for force control, you need something like 1 kilohertz update rate. You want to have something stable. And then you have the latency problem. If you are transmitting data over a network, then you are putting latency in the control loop, and you have to solve that. Then you have safety constraints, and that's when you want to go to the market with a telerobotic solution. Safety for the operator, so you can do that by reducing forces and speeds of the master robot. You can monitor the activities so that you will do basically emergency stop if the software sees that something wrong is happening. And on the remote side as well, you have to control the forces and speed of the slave robot so that it doesn't wreak havoc in the environment. And finally, something you also have to face when you want to go to the market, you have standards to consider. So for example, there's a new standard 15066 robots and robotic device collaborative robots, which is now in force, and you have to see how you can adapt or apply that standard. And maybe if you should also look at something like the 13482 about safety requirements for personal care robots as probably the future standards will incorporate some of those requirements. So a lot of things to consider when you're developing a telerobotic system. So what's now the vision of Haption with respect to that? And that's a chart which is a bit complicated. This is a view of our coming product, which is called Telerobotics Extender, or the short name T-Rex. This is the view with collaborative robots. So collaborative robots are very nice if you talk about telerobotics with force feedback, because they already incorporate force sensors and in some way a kind of force compliance. So we're looking here, for example, at the E series of the universal robots, the 5, 10, 16 now. We're looking at the KUKA Iwa, which was the first on the market as a collaborative robot with joint torque sensors, and now a more recent entry, the Kinova Gen 3, also redundant, like the KUKA Iwa. The way we see it, and after compiling lots of requirements from different customers, is we want to not only to have master-slave control over a network, internet if the ping is good enough, 5G is coming. We will have use cases where we need a radio frequency transmission, maybe Wi-Fi. So a variety of transmission solutions with different latencies, different loss rates. And the way we think we need to solve that problem is to have one component, one intelligent component at the master side, one intelligent component at the slave side, communicating with each other so that they can measure latency and compensate it. And that's the core of our expertise at Haption. That's what we can deliver. but it shouldn't be a closed solution. So we want to have external APIs or external or data streaming, so that customers can develop their own user interface or can interface with a ROS solution, for example, or add some sensors on the slave side as a laser dyer or whatever. And on top of that, we also want to include the possibility to stream video data through our connectors, so as to simplify first the implementation by the customers. They don't have to care about, well, they don't need to care about installing a video solution themselves. They can use the streaming available. And also, we plan to have a way to manage priorities between the control data and the video data. There's also another added value, which is that in case the video link fails, the connectors will know it and they will be able to stop the motion while the operator is blind. So that's the whole concept for collaborative robot, as I explained, and that will be providing dynamics feedback, but also interactive feedback, meaning a really interaction with the environment. But then this is only for collaborative robots, and there are lots of use cases around which don't fit those collaborative robots on the market today. And so we also plan to have an extension for industrial robots. So we already played around with the KUKA KRC. We already played with the Kawasaki robotic solution and another number of suppliers. We're already confident that we can handle those two, for example, but only with dynamics feedback, meaning that they do provide a kind of high-speed interface, but it's not really 1 kilohertz, and so we are not going to have a dependable systematic interaction feedback with force measurement. It will be possible case by case, some with the measurement of the motor currents, some with additional force sensors, but it will always be a specific development. So we also plan in the future to talk with Dobly, ABB, Comau, whatever, depending on the use cases and the requirements of the customers. And then there's a second extension again, which is the possibility to have a custom designed slave robot. And this is a case we often see in the nuclear industry, having a legacy telemanipulator which needs to be motorized and used as a slave with our virtuous devices as master. And for that, we are also developing a connector for the Yaskawa series of products, the Sigma 7 motor drives and the SGM7 servo motors, which have very strong torques and a good control flexibility with a CAT bus, so we can basically put the Sigma 7 motor drives on the bus, as many as needed for the slave robot. And as long as you choose the motors from the Yaskawa series, you can drive your own robot. You just need to define your kinematics, and that's it. You can tune your control loop directly with the Yaskawa software, which is very efficient for that, and drive your robot and have your master-slave control system with our Telerobotics extender. So that's our vision. That's coming soon. We will have a first version of T-Rex coming up end of June. But now let's look at use cases. So first, I will show you 3 successful use cases already around. in the field of nuclear energy and healthcare, and then talk a bit about future use cases which we see coming, especially with the advent of the new collaborative robots and the new high-speed interfaces with the industrial robots. In the case of the fuel processing or fuel reprocessing in the nuclear industry, robots have been used for more than 60 years for handling radioactive material. Most of them were initially mechanical telemanipulators, which are very good at what they do, but are very expensive to maintain and have their mechanical limitations. So the benefits of replacing those or enhancing those with a force feedback master slave control is to have a better economics and lower maintenance costs. So here is a short video of a test bed at Orano in France. That's the fuel reprocessing company. You see here, sorry for the French, but that's Orano video. Really, you see all the functions of our VITOS device, which on the handle we called tray. So you can, of course, you have a trigger to control the gripper. You can lock the gripper. You can rotate it without moving your hand, and then you have additional functions on a small box at the forearm to control different functions. And here is what is the example of a redundancy on the elongation of the third joint. Sorry. So that was about fuel reprocessing. Another example is for decommissioning. So here again, it's about handling radioactive material or cleaning up or cutting the facility, basically to extract the parts which are decontaminating and then put them in a bin. The alternatives are to work with an environmental steward, which is a very difficult activity, or you can also, of course, place a robot and program it, which takes a lot of time and makes only sense if you have operations which you have to repeat over time. The benefits again of force feedback is to reduce the contamination hazard. That's mostly for, well, the telerobotics in itself, but also having force feedback, specifically will enhance the safety of the operations, because you control really what you're doing, how the robot moves. So here an example which was shot. Well, that's myself moving. So I'm not an expert nuclear teleoperator, just showing the capabilities we can reach with this KUKA industrial robot. So compared to fuel processing, where the intensity of radioactivity is extreme, in case of decommissioning, there are some areas where well, those areas where potentially you could send human operators, where the radiation hazard is not too high, and so you can also implement standard industrial robots, but you need a way to control them remotely, and that's an example with a simple KRC controller. Another application or use case is in healthcare to provide remote services. Well, it happens that with the running pandemic, this is a very hot subject right now, but it was not invented this year. And a number of our customers have been developing systems for remote diagnosis, for example, echography. So The alternative is that, and that's what being done today, is that the physician drives to the patient, or the patient drives to the physician, to the hospital, or whatever. And here, if you replace that with a telerobotic solution, then the force feedback gives you a higher safety and confidence for the patient and for the physician, because they are really controlling the force applied on the probe. And also you have better precision of movement, because the force feedback also reduces your motion speed, and you can scale up and down your motion. So that's specifically developed for areas of low density of medical facilities. And here, an example of the ROSE project in Portugal, where they really in that case implemented one of our Virtuos devices as a slave. As you can see, this is a Virtuos 60 device, and they're using our Virtuos 60 desktop device as a master. And so you saw really operation on a real patient. The project is running, and they are looking for market introduction coming soon. Now I'm moving to the future use cases. Some things which we've been discussing with customers as prospects, but we have not hard data on. So first example, in the manufacturing industry, the problem of live maintenance. It means performing small maintenance operations without stopping the production. And when you've seen big automotive factories, you see all those robots in robotic cells. The cells are closed, no human is allowed inside. And so if you need to do maintenance there, you have to stop the production line. And usually, basically, you wait until there's a holiday period, or where the factory the line is closed anyway, to do all the maintenance stuff there then. So or you could use an autonomous robot, but that's a problem which is technically not solved. So the benefits of telerobotics with force feedback is to be able to do the maintenance remotely without stopping the production. Remotely is, in that case, in very short distance, so you don't have a problem with latency. And the benefits of force feedback is that you have a better control of your process, of the forces you apply, of your motion, and also you can be assisted with virtual fixtures. So here is not a real use case, it's just a demonstration in our factory in France about controlling a new universal robot. This is a UR10E with a force sensor, and doing some different stuff which you obviously could not program because the environment is just not fixed enough for having set positions, and you know, it's just a rough handling, which is just not programmable. Another example is remote maintenance for the offshore industry, where you have delicate maintenance operations to be done on the offshore platform, which requires a specific expertise. So today you have no alternative but flying an expert to the platform, which might be difficult depending on weather, depending on the distance, whatever. And so using telerobotics to do that, meaning that we will need personnel on the offshore platform to set up the robot, probably in the right place, but then the expert can control from the distance. And here an example, again, not a reuse case, but showing that what we've done with Kawasaki Robotics about controlling a small robots, which could be easily used for such kind of remote maintenance on site. Here, Pierre moving the with our Virtuos 60 TAO device with the tray handle. So you see that we can have a very delicate motion, and here you see that we have a scaling of the motion. Pierre is doing a lot of clutching to recenter the master device so that he's always in the right position, the optimal position to control. Another use case we've been discussing is for chemicals and pharmaceuticals, the use of glove boxes. Glove boxes are widely used in lots of industries, using robots in glove boxes would be a way to reduce the risk to human operators and also to optimize operations, because they would not always be limited to the ports, the entry ports, which have been placed for humans, obviously. And again, here, an example of using a Kinova Gen 3 robot in a horizontal position so that it could be inserted through an existing port of the glove box. Again, with the same virtuous TAO with a tray handle inside our factory. And one final use case we've been studying is clean rooms for microelectronics and also for pharmaceuticals industry. So clean rooms are also widely used in those industry, and again, the process for humans to enter and exit is complex, takes time, and also the risk of contamination is high. So having a robot replace a human in an environment which was prepared for humans, so typically a humanoid robot would be suitable for that. That could help have a better control of the process, and also have an increase of productivity, because the robot doesn't have to leave the clean room every 2 hours for having a break, and also reducing the safety hazards. So that's an example coming from one of our customers, NTT Docomo in Japan. They were showing 2 of our devices controlling 2 arms of a humanoid torso at a trade show in Japan. And here, I switched off the talk because in Japanese, but here you see the person having a very nice display, semi-transparent, and the robot acting on the other side with force feedback, with very complex tools. So it looks like a prototype, of course, but this is coming up. And here you see the importance of having this dynamic feedback so that you really control the fine motion. So that is for the use cases. The key takeaways I want to point out are, so Telerobotics, I told you, is an old concept. 8080, the first papers of Thomas Sheridan. Yet now we see it undergoing a rebirth, thanks to many emerging use cases, and also thanks to the availability of those nice collaborative robots with force sensors and high-speed interfaces. The force feedback itself plays a key role in Telerobotics because it helps you better control. That's what I call the dynamics feedback, and also it helps you sense the action of the robot on the environment, and so reduce its potential negative aspect. So that's what I call the interaction feedback. And both are important, but sometimes even if you have no way to measure the force on the environment, even dynamics feedback is already a very good added value. And finally, master-slave control is at the core. So that's really the robotics aspect. but then it's useless if you don't have all those other functionalities like scaling, clutching, viewport management, interleaving with automatic modes, so switching back and forth between manual and automatic. If you don't have little features, complexity, latency, etc. So that's a whole bunch of complex issues which need to be addressed, each of them separately. So basically, it's all about leveraging your manual skills with robotics, and that's what I wanted to tell you about today. Now, Pierre, maybe you want to introduce the Q&A. Meanwhile, I have a small demo here behind me, which I can show you while you type your questions in the chat. Last time we forgot to explain that you can raise my my video on your screen. I think you just have to double click on my picture, and maybe I will quit the screen sharing so that it doesn't disturb at the same time. So if you, and so let me introduce my haptic device here. So this is a Virtuo 6D TAO that's with this button box here at the forearm, which gives you lots of further control on what you're doing while controlling the robot. And this is not a tray handle, this is the simple Cobra handle with 3 buttons, but it works as well in this case. At this moment, the motors are switched off, then you first see that it doesn't fall down. So this is what we call the static weight balancing. We have springs in the base, which here.
Yes, if you want to visualize the image on the full screen, don't double click, it didn't work. You need to go in the middle of the screen on the top, and you can change the way that the different window is visualized, and you have on the second, you have the people who is talking and who will be on your full screen.
Okay, thank you for that. Yes, back again. So we have springs in the base which compensate the weight. So now I will switch on the motors and grab the handle. The handle in this case has 3 buttons at the top here. The middle one is the clutch, which I will explain. The others can be affected as you want. And at the below here you have an optical sensor, which is the dead man switch, which means that whenever I let go of the handle, the motors are switched off. This is a hardwired safety for the operator side. And then I have here a simulation. I'm afraid the sun is shining on the screen. I will try to turn it a bit. Maybe a bit better now if I move to the side. Yes. Here I have a simple simulation of a robot. So this is a use case in nuclear industry, but the simulation is not really operational. In a case, it's not an operation I would have to do in a nuclear cell. I also have here a small tool, which is a camera, which is showing different views. Well, the bottom view, which is in the sun, shows you the view of the video. And what I want to show here is first the force feedback. So here, when I'm hitting the table with the slave robot, the Virtuos resists, and you can of course not feel it remotely, but you can see that everything is shaking because I'm pushing on the table and the screen is shaking. This is really the force felt fed by the Virtuos. And here I have a simple simulation with wooden cubes which I can push around, let fall, and pick up. So the important functions are, of course, this force feedback. Then the clutching, which helped me reposition my hand whenever I want to have a better reach, for example, to go all the way to the end of the cell, which would otherwise be inaccessible. And then I have buttons, in this case, for opening and closing the handle, because I don't have the trigger of the tray handle. So that's a short walkthrough of this application. I'm sorry, I don't have a slave robot here in real to show you.
Thank you, Jerome. So now we go to the Q&A. For now, there are nothing. So please, if you have any question, write in the chat part. It's on the right part of your screen.
No questions?
No?
I talk too much.
Yes, one.
Oh, yes, one. I'm reading the question.
Yeah.
Could you please talk a bit about the control strategies? Is the master being driven with positive feedback to make it feel loose? What other consideration do you have in terms of deliberating force feedback in a master-slave setup? So the strategies, so of course, part of it is core to our expertise, so we won't give it away so easily. But basically, what we're doing is what we call position control, meaning that the Cartesian pose of the slave robot is sent to the master robot, and vice versa. So the Cartesian pose of the master is sent to the slave. And if you have a slave robot and a master robot, which are both force compliant, then what you achieve is a practical teleoperation with force feedback, so with the telepresence aspect. So that's the basic idea. This question about positive feedback on the master. So we do have some latency compensation, which is part of the answer. But also, if you want to have a very transparent, meaning good transmission of the information, of the force information in both directions, you will need to compensate a number of friction and inertia parameters on both devices, not just on the master. You also have to take care of that on the slave. And then what other consideration do you have in terms of directing force feedback in a master-slave setup? This is a lot of things that you learn by doing. For example, if you are implementing the clutch, as I showed, clutching is just like lifting your mouse. It's just separating the connection between master and slave for a while, so that you can recenter your handle. If you do that without thinking, you will lose the force of the force feedback of the slave robot. And if the slave robot is currently doing something with a heavy tool, then what happens when you release the clutch is that you get the full force at this back, and then of course you drop and you break the tool on the slave robot. So this is a simple thing which you will discover when you do it first. So first you will break your tool, yes, but then you learn and you implement solutions for compensating for that. So that's also a part of the things you will the expertise that we bring with this Telerobotics extender, that we have learned all those difficulties and implementing solutions already.
Thank you for the question. Any other question, please?
You're welcome. It just says thanks.
Yeah, nothing else?
No question? Okay.
Okay, we will close. What we will do, we have done a record of this seminar, so we will send you first the PDF of the presentation and also a link on where the video is available for you to show or to share. Thank you very much. Thank you for your time, and have a good day for some, have a good evening for some others. Thank you.
Thank you. Bye-bye.